Thanks for voting, Matt. Here's your video.
Cyclotrons are a type of particle accelerator. They can be used to accelerate charged particles to very high kinetic energies. These circular particle accelerators are sometimes huge, like the Large Hadron Collider at CERN. This is the world's largest and most powerful particle accelerator, 27 kilometres in circumference and more than 2 kilometres across. Others are much smaller. The cyclotrons that are used in hospitals to produce radioisotopes with short half-lives like fluorine-18 for using in PET scanners are more like this size. So in a hospital cyclotron, you'd find two hollow D-shaped metal cavities called Ds. These are inside a chamber and there's a vacuum. That makes sure that there's nothing the charged particles can waste their energy on ionising or colliding with. A magnetic field is applied at right angles by powerful electromagnets, and it's this magnetic field which provides the centripetal force to keep the charged particles moving in a circle inside the cyclotron. The source of charged particles start at the centre of the cyclotron. So for our hospital cyclotron, thinking about making fluorine-18, the proton source that's needed starts at the centre. As these protons gain speed, they move in larger and larger circles, causing the spiralling out path that you can see. Once the particles reach the outer edge of the cyclotron, they're at high speed and have high energy, and it's here that they exit the cyclotron because there's no magnetic field to hold them in the circular path anymore. So you can see they come out in a straight line at high speed, high energy, and they can be aimed at the target. In the case of the hospital making fluorine-18, that target would be oxygen-18, so that they could be bombarded with the protons, absorbed and produce fluorine-18. But this magnetic field that's keeping the charged particles in a circle isn't actually accelerating them. To accelerate the charged particles, electricity is used. The Ds are connected to a very high frequency alternating voltage, which repeatedly changes the polarity of the Ds. This has the effect of pushing the particles from behind at the gap between the Ds and pulling the particles across the gap by attracting from in front. So let's say it's protons that are being accelerated in our cyclotron. They'll only be accelerated across the gaps between the Ds, so twice in each full circle. At the gaps, to accelerate a proton, you're going to need a positive charge behind to repel the proton and push it away, and across the other side of the gap, a negative charge to attract them and pull them across. That will accelerate them. Each time the charged particle reaches the gap between the Ds, they gain kinetic energy as they're accelerated across the gap. You could actually work out the kinetic energy of the particle, because if you know the charge of the particle, you can times it by that accelerating voltage across the Ds. That would be the same as working it out by knowing its mass and its speed by doing half mv squared. Does that ring a bell? Because you have seen it before in the electron gun equation, when we're accelerating electrons as our charged particles across the electron gun or the X-ray machine. Sorry, I digress, but isn't it lovely how bits of physics will just come together? Sorry, right. To keep accelerating these charged particles in our cyclotron, the polarity of the Ds has to keep changing so that it's always pushing from behind and pulling in front across these gaps. Let's recap. So particle accelerators use charged particles. If the particle had no charge, it wouldn't be held in a circle by the magnetic field, and it wouldn't be accelerated across a gap in the Ds by an electric field. The magnetic field keeps the particle moving in a circular path by providing the centripetal force. The high frequency alternating voltage accelerates the particles by repelling and attracting them across the gaps. Once the particles reach the energy required, they're collided. So in hospitals, this collision involves bombarding a stable isotope to produce an unstable isotope, using the high energy charged particles collide with something that's stable to produce a radioisotope with a short half-life that could be used in diagnosis, for example, with our protons bombarding oxygen-18 to make fluorine-18, our beta plus emitting radioactive isotope that can be used in PET scanners. So at CERN, the collisions involve extremely high energy particles colliding with other extremely high energy particles. Smashing these particles together is helping us to try and discover new subatomic particles and fundamental particles. In hospitals, the particles don't need to reach anywhere near that high energy that's achieved in the Large Hadron Collider, which is almost the speed of light. So they don't need superconducting electromagnets, teams of scientists and engineers to operate and analyse everything. They don't need to be as big or complex as it is at CERN, where the particles are actually accelerated in several smaller accelerators before they even get to the Large Hadron Collider. So that's it, cyclotrons. I hope the video was useful. I hope you're still revising, because you know that
regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics,
subscribe.
so you can get notifications of when my next video gets uploaded.